a low carbon world, a zero carbon world is what we need. And of course, technology is going to help us to do that. And I'm thrilled to introduce to you 4 people that are going to take us through the next hour or so, initially with some of their own thoughts. They're going to be here for 5 or so minutes each, talking about things, and then we're going to have some questions and everyone can contribute to that. The first person to introduce is Edda Aradottir. Edda, are you here? Co-founder and CEO at Carbfix. Edda is a chemical engineer and she works, completed her PhD in reservoir engineering in collaboration with the Lawrence Berkeley National Laboratory. Thank you, Edda. We have Francis Wall, please, Francis. Professor Francis Wall from the Campbell School of Mines at the University of Exeter. She specializes in technology of raw materials, especially rare earth elements, lithium and cobalt, needed for decarbonizing. Thank you. Then we have Friedrich Bohn. Friedrich, please come up. Friedrich investigates future dynamics of ecosystems at the Helmholtz Center for Environmental Research in Leipzig. And Matt Green. Matthew, please, Matt, come in. Is an associate professor with tenure within chemical engineering at Arizona State University and director of the Center for Negative Carbon Emissions. Please. Wonderful. So that's our panel. Each of you are going to come up here for a short while, say a few words. I think the first person we've got is Edda. Please come on. Wonderful. We've got a roving mic as well, which I'm going to catch, and I'm going to go around the room when we do have questions. But we'll do those questions at the end. So we'll do 5 minutes each or so. Then we'll do group questions, and then we'll do a wrap up. Okay.
Sounds good.
Great.
Sounds good. Good morning, everyone. Yeah, I wanted to just take a few minutes to give you an overview of what it is that we do in Carbfix, the company I lead. Basically, we turn CO2 into stone, CO2 that's been captured either from point source emissions or directly from the atmosphere. And we then use our process to permanently transform it into minerals underground so that it's out of the picture more or less forever. So I have a few slides. And this one states exactly what I just said. What Carbfix does is capture CO2 and turn this captured CO2 into stone underground. And this happens by use of our process in less than 2 years, which significantly speeds up this process. This is already happening in nature, has been part of the global carbon cycle for millions of years, but typically in nature happens much, much slower. So by introducing our technology, we make this happen in just 2 years, which is, of course, what we need. We need to make these processes happen much faster. And how do we do it? Just explaining the technology in a very few words. We can do it. We have 2 models that we implement. We can do it in a single step, capture and injection, more or less just in the same step. And this is what we have been doing at our site in Iceland, where this all started close to 20 years ago now, then with just an idea on paper. At this site in Hellisheiði, we have the largest geothermal power plant in Iceland operating, and we have some volcanic emissions of CO2 as a byproduct of the ongoing energy production. So we developed a process that allows us in the same and single step to capture otherwise emitted CO2, basically by taking the emissions from the power plant through water scrubbers. Very simple technology. Just take the emissions through a shower, and the CO2 and actually also hydrogen sulfide, which is also a byproduct of the ongoing energy production, they are automatically just dissolved into the water. And then this is what we inject into the subsurface. Basically, what's the, sorry guys. Yeah, basically we inject sparkling water. Sparkling water is the name I was looking for. Sparkling water with a sort of a geothermal taste, if you will. It's not very good, but that's in essence what we are injecting. dissolving CO2 in water, H2S as well, on the surface, and this is what we inject then into the subsurface. Then we can also link the injection part of the technology with third-party capture solutions. It can be DAC, it can be third-party solutions for point source capture, but the injection works more or less the same, but we still transform the captured CO2 into sparkling water, but then we do that on the way down the well. So then you can sort of think of the well infrastructure as a soda stream machine. And why do we dissolve the CO2 in water? Well, it's because of mainly two reasons. Firstly, because having the CO2 already dissolved in water allows the natural reactions that then happen in the subsurface to happen at a much larger speed, because these are happening between the water phase and the host rock. So by already having the CO2 dissolved in water, that is how we speed up this natural process, allowing the mineralization to happen in just 2 years instead of over a much longer time frame. And then the second reason why we dissolve it in water, while either prior to or during injection, is that then we eliminate the buoyancy force of CO2. If we were injecting a pure CO2 phase, it's buoyant. It wants to rise to the surface. And in Iceland, where all of this started, we have very young rock formations. We don't have any tight cap rocks or anything like that would make sure that, in spite of the buoyancy force, the CO2 is not released into the atmosphere. So by having the CO2 dissolved in water, we kill this buoyancy force, make sure that the CO2 stays fully dissolved in the subsurface until the 2 years have passed and it has mineralized. The water is not lost in any way. It acts as a carrier for the CO2 while these processes are happening in the subsurface. And then we can use the same water again and again if site conditions allow for it. And where we have been operating this process now for more than 10 years, we have recirculated the same water. Last time we counted over 13 times. So even though we require water for the process, we don't lose it. So highly flexible process and technology, allowing us to implement point source capture just in the backyard of locations where emissions are taking place, but then also building more complex value chains where we are not able to inject in the backyard of such facilities, but adding transport links of captured CO2 over much larger distances. And here we should have a video. No, the video is not working, but it's basically should be showing that we have these different value chains allowing us to, as I just said, either build out the infrastructure just in the backyard where we have emissions or capture taking place, but then also add transport link over significant distances, even across oceans. We have a project like that under development in Iceland, allowing us to take this technology to the megaton scale. We're currently operating at the kiloton scale per annum, I should add. But irrespectively of how we build out these value chains, if it's point source, if it's point to point via transport, we always do the injection the same way, as I have described, dissolving the CO2 in water, killing the buoyancy force, speeding up the mineralization reactions that then permanently transform the CO2 into stone underground. And we need to inject the CO2 down to approximately 300 meters. We can go deeper, but at minimum, we have to go down to 300 meters to make sure that the pressure in the system maintains the CO2 fully dissolved while it is mineralizing. So this all started in Iceland as an international collaboration between Reykjavik Energy, the largest geothermal energy company in Iceland, the University of Iceland, Columbia University, and CNRS in France. That was back in 2007. We wanted to make sure that by the time the world would catch up, that indeed we need to do something about climate, we would have a solution available on the shelf to implement, to take to scale. And we're there now. We have been, as I say, developing this technology for 20 years, close to 20 years. It's been operating under commercial conditions for more than 10 years. It's fully scientifically proven. It's independently verified, robust MRV processes associated with all of this. We are operating in relation to point source capture from energy production. We have been operating in relation to direct air capture for more than 5 years as well. And where do we go from now? Well, we're ready to take this technology global because these favorable formations that we target that rapidly mineralize CO2, they are found not everywhere, but in many locations around the world. And on our website, if you use this QR code and have a look at our website, we have a map that allows you to see where around the world do we, for example, have basalts that are a rock that efficiently mineralizes CO2. Such formations that cover about 5% of the continents, majority of the ocean floor. And if we look at the capacity at which we could be mineralizing CO2 in these formations, it's orders of magnitude larger than ever needed for climate action. So the potential is absolutely there. And we are seeing countries around the world really building momentum in scaling solutions like ours. And we need to make sure that we keep that momentum going. So to sum it up, what we do in Carbfix is we permanently mineralize CO2 underground. The technology offers clear competitive advantage compared to alternative solutions that also do indeed inject CO2, but not for mineralization, typically just to store a pure CO2 gas phase. So what are these competitive advantages? Well, it's permanent. Once we mineralize the CO2, the rocks that form there are stable for millennia, just becomes part of the bedrock and don't have to worry about it anymore. No need for long-term monitoring, long-term liability, the same way as when you're storing a pure CO2 gas phase. It's safe, it's verifiable, because we dissolve the CO2 in water while we inject it or before we inject it. We have instant solubility trapping of the CO2, eliminating any risks of leaks. And as I already mentioned, fully measurable, third-party verified, so robust MRV technologies already developed and demonstrated, which is critical, of course, for operations like this. It is a highly efficient and cost-effective solution, requiring low energy input because we operate under low pressure. We don't need to inject deep into the ground, as I mentioned, only a few hundred meters. And we have a proven cost-effective deployment at a much lower cost than alternative solution. At the power plant where we have been operating this for more than 10 years, we have the full value chain operating at $30 per ton. So for capture, injection, monitoring. I know, it's amazing. I should add that in that case, we have a concentrated stream of CO2, meaning that the capture is more efficient than when it's dilute, but it can be done and it is being done. And last but not least, scalable across the globe. So that's what's next, to scale across the globe. Thank you.
You read it. Next up is Francis Wall. Francis, please.
Oh. Yeah, it's just coming. Right, so I'm going to stay with the geology theme here. So it's the underground people up first. And I'd like to talk to you about the critical minerals. And of course, they always seem to be in the headlines at the moment. So I think what's on the news streams at the moment, it's about China, isn't it? They have restricted the rare earth supplies for magnets. and the world's car manufacturers are in trouble. So there's had to be lots of negotiations between the US and China to sort that out. It's part of the trade and tariff war. And that's the critical minerals threat side, right? Okay, so I'm not going to do geopolitical threats today. I thought what would chime better with this conversation is to go to the opportunity. So with every threat that there is in the world, there is definitely an opportunity too. And I thought I'd show you some examples of this morning and see what discussion that picks up. So with the critical minerals agenda, then, we're talking about the materials, the raw materials that we need to make the technologies to combat climate change. And we're usually talking absolutely about these renewable energy, low carbon technologies here, like on this slide. And I kept the mobile phone on this slide because all the tech has so much electronics in it that electronics just applies to everything now, doesn't it? I haven't got carbon capture and technologies on here, so it'd be interesting to know what raw materials or specialist raw materials are needed for those technologies, and we can add them in for the future. But this is about the scale up of these tech and how we're going to resource what these things are made of. And can I just divide what they're made of into two? There's the really super important major materials, especially metals like steel, for example, or copper or aluminium. And they're mined in at least 100 times more, if not thousands or more times more, than the other things that you need to make these things work, which are the really specialist things like neodymium or indium or even tin that you will have heard of more, some elements that people have hardly ever heard of. And yet without these strange elements, we're so clever at making materials now that need these special properties from special elements that even if these things are only mined in one or two places in the world and that can supply everything we need, they're absolutely essential for making these things work. And that's where the original critical raw materials or critical minerals agenda came from in about 2010, 2011, with lists from Europe and the USA of these really specialist raw materials. But today, in 2025, here's my periodic table of criticality. And if you take out the things that don't exist in nature, you'll on the bottom of the table there, you'll see that actually one way and another in the UK list, which is in blue, and then the additions that are not on the UK list last year, but in Europe or the USA, that pretty much covers the rest of the table. So from just a few things, 14 on an original EU list, what the critical minerals agenda has done is to prove to us all how much we really need these raw materials. And when we say critical minerals, some people get really cross about that, the materials scientists, because minerals are the natural materials that come from the earth. It's like vitamins and minerals, really. We're talking about these elements that go into the technologies. And I'm going to start from the beginning because we know we need to bring a lot more of them into the value chains. But I absolutely want to say that when we've got them, we need to look after them so much better than we do at the moment. And what we need is new circular economies. So we need to mine them in the right way to begin with, and then do all kinds of clever things with the manufacturing and the onward stewardship and eventual recycling to look after them. So that's one challenge we might pick up. But I thought I'd just show you a rock, first of all, to show you what the critical mineral really looks like. And this is a rare earth ore, so nice and topical. That's a backscattered electron image that you're looking at. And these tiny little crystals, the white ones are the rare earth mineral, trips off the tongue, synchesite CE it is. Right, I could lecture you for hours on these minerals if you would like. But they're tiny little plates cut through here, and the scale bar is 0.1 millimeters. So the challenge here, there's a huge technical challenge, is to separate out the mineral we want from all the other grey stuff that we don't. So first of all, there's good circular economy here. What are we going to do with all the other stuff? It's not just a matter of what we want. And then we say rare earths. What we really want here from Malawi is neodymium and maybe tiny amounts of dysprosium and terbium. And so there's going to be oversupply of lanthanum and cerium. So we need lots of new technologies to do things with the rare earths in oversupply. So it's quite a complicated picture from the technical side. And this is a company based in the UK that's been exploring in Malawi for about 15 years and has now got its final feasibility study and is ready to go. And so this is a really important point. If they get this mine open in southern Malawi, they think it makes about $100 million contribution to the local economy each year. And I don't know whether that sounds a lot or maybe not a lot, but Malawi's economy is so small that I assure you this is a total revolution for the whole country of Malawi if this mine can raise the investment it needs. And, you know, that's a big if still, even after all that work and all the work with the local communities there. And so this business about fairness and who benefits from the critical minerals agenda around the world is really important, but it's not just a developing country agenda. It's an agenda right here. Here is southwest England, where we are in Exeter today. And we have some granite rocks here that have been mined actually for 4,000 years, come to think of it, for copper and tin. But here now we have 7 companies exploring for tin, tungsten and lithium, all critical minerals that we need, and the potential for joining up supply chains to battery manufacture and recycling in a circular economy. And how we do that now, whether we can get it going, whether we can make it economic with low enough energy costs and things, and get that all to work for everybody, is a really important area of research that we're involved in at the University of Exeter. And here I mean, it's not just that we ought to do it because we've got some deposits. We have the second largest resource of tungsten in the world here in southwest England. So there are some quite serious deposits. And I think the point here, we've forgotten about that. I would say in North America, except for Canada, in Europe and the UK, we think mining is something that we used to do. But actually, we need to think again and bring it back, maybe on different scales to the kind of huge copper mines in Chile, for example. But how we get this going now is really important. And these are technical challenges. So here we go with some new core, we're working on the geology and so on here, but also looking at the old waste and whether we can take that around again, or rather whether we'd rather have it frozen and preserved in our UNESCO World Heritage Site. So really transdisciplinary research that we need, because at the base of the fairness point here is some of the most deprived areas in the UK are actually in some of the most beautiful areas in Cornwall here. And how can we really reach these people to really level up the livelihoods and make really good jobs? We always talk about this in mining, there'll be great jobs for people. But what are really the good jobs? And this is the kind of transdisciplinary research that we're doing here at the university. I think it's a really exciting challenge. And it's great that we can do it on the other side of the world with colleagues, and we can do it right here at home. Right. Thank you very much, Martin.
Thank you, Francis. Next up is Friedrich Bohn. Okay.
So thank you very much for being here. And I had yesterday a lot of very, very inspiring discussions already with some of you. And I really love the place. It was really nice. And I also really love the stories about Cornwall. We learned yesterday, starting from the Roman Empire, which come here to investigate in the sources you find here. And what I like in the story yesterday about Cornwall is that it looks back, but it also looks into the future, like a Janus-shaped hat. So you have to, I think, you have to look back in history to really get new inventions for the future and to solve problems. And I want to share with you our story about, not about Cornwall, but about construction and the history of construction and the future of construction. And I will go even further back, not only to the Roman Empire, but back to the Neolithicum. Because when we left the caves, we start building first construction things like huts out of wood, because this material was everywhere more or less available. And then humans decided, okay, this is very nice, but maybe we need also another material which we find out there, and this is stone. So mankind uses stone to construct more buildings, larger ones, because you can construct larger buildings with stone. And the third invention which was made is using adobe bricks. So in the first time they were just dried in the sun, But then also you discover that you can use these bricks and burn them, which of course you see here, and then the problem starts. You emit CO2 by burning them, but nevertheless, the good thing is they are quite like modules. You can just combine it and create different shapes very easily. And then I think there was a really great invention several hundred years ago, which is this one. So the framework architecture, which combines different techniques. So you have wood on the one hand side, you also have bricks to fill the gaps. You use stone for the fundament or the basement. And these new construction materials in their time, they were really modern, they were really innovative, and they were also quite cost effective for this time. But then there's the twist in the story, because mankind developed this one, which is ferroconcrete or reinforced concrete. And at the beginning, human thought, oh, that's a nice idea, because we could now make really crazy, cool constructions and build huge bridges and skyscrapers, etc. So a high performance material which outcompetes the other three. On top of that, it's very easy to create a mass production. I mean, you just build these ironworks, you create these plants which create the cement, and you can really, I mean, just look at the world, how fast you can construct whole cities with it. And on top of that, it was also very cost attractive, at least in the beginning. But now the tide is changing, and I would say, well, we now have the problems of the corrosion in this material. I mean, probably you remember this collapse of the bridge in Italy, where a whole motorway bridge collapses into a city. This is a picture from this event, because the lifetime of ferroconcrete is around 30 to 40, maybe 50 years, depends a bit on the construction. Of course, because of this mass construction, the production of ferroconcrete is responsible for roughly 10% of our CO2 emissions, and we have, until now, no clue how we can replace it, because we need the infrastructure, right? I mean, we need the bridges, etc. And on top of that, the prices will rise in the future, because the production of iron is very energy intensive. Also, sand, what you see here, is getting more and more expensive, because the sand you need for ferroconcrete is diminishing. And so looking at this list of 3 different problems, the company I'm working on, collaborate with, well, thought about it, and maybe we should, well, we have to solve it to a certain degree. And so they made several inventions. And the first one was to create a very light material which has the same performance like ferroconcrete. So you can really measure the pressure resistance, the tensile strength, etc. It's more or less like ferroconcrete, sometimes even better. And on top of it, the weight of this material is only half of ferroconcrete. Then we have this problem with the CO2 emissions, right? So the idea was, okay, we need another invention where we combine different techniques. So we combine the concept of enhanced rock weathering in an innovation, and include also the biochar application. And we also include BECCS in the way of that we use a material which allows, or which uses photosynthesis to capture CO2 from air and create a new material out of it. And last but not least, we still have the cost problem. And we found out, making a technical economic analysis of a new material, that it has the same price as ferroconcrete. So we are in the same magnitude. And on top of it, because you can sell the carbon fixation of this product, you can even make money by selling CO2 certificates. So my take-home message, at least, is remember a high-performance, light-weighted material. The method combining different CDR techniques together and make a fusion out of it, and be very cost-attractive. And to be honest, these are not 3 different inventions. It's only one. So we combine everything together and creating the so-called carbon fiber stone, which is made out of basalt. And as you have seen in the Edda presentation, basalt is more or less everywhere available. So it's a huge resource or stock which we can use even larger than the limestone you need for the ferroconcrete stuff. Within the wall, there is biochar helping to isolate walls in a fair manner. It's lightweighted, it's much lighter than ferroconcrete. And on top of it, to get the tensile strength, we combine the stone with carbon fiber made out of algae, and it's also possible to make it out of lignin, which is a byproduct by producing paper out of wood. So here you see we combine stone, photosynthesis, or wood, and during the production process, you create stone powder, which you can put on the soils of the world as a fertilizer, which also fixates carbon. To sum up, so this is a science-based product. We published all these inventions in a paper 1 month ago. The material is already awarded by the JAC Award 2025. It has a high performance, as I told you. It is very lightweighted. It's low tech, so to produce these things, you don't have to build such a huge industry of iron works and other power plants. You can just create it in a room like this one. So you need only a few of machinery. It is CO2 negative. So for 1 square meter of a building, you would fixate 100 kilograms of CO2. And if you scale it up, I mean, just imagine if you would replace all ferroconcrete on Earth with this material, we would fixate every year 40 gigatons, which is 10% roughly of the emissions. As I said, it's cost attractive, and it's still in the beginning. So there is still the possibility to reduce the cost further, because the current situation is we are working it's handmade. But if we increase the industrial production, if we increase decrease the raw material production or reduce the transport lane, because the material is everywhere available, we could even have a price which is similar or even lower than ferroconcrete. And last but not least, this material is globally patented, so we are ready for investors. And I think maybe it's not the silver bullet, but maybe this is another bullet for the silver bazooka, and we now have to just shoot around and solve this fucking problem of climate change. Thank you.
Thanks, Friedrich. Perfect. Just a clarification, 40 gigatons, that's all of the carbon that isn't it? So do you mean four? Yeah. I thought I thought there was a silver bullet for a second. I thought we'd done it. I thought we cracked it. No, yeah. Wonderful. Next up, Matt Green, please take it away.
Thank you, and thanks for having me. I like your silver bazooka as well. So today I'll tell you about the work we're doing in the Center for Negative Carbon Emissions, developing different direct air capture technologies. And I just want to quickly highlight our mission statement. So I took over, I'm Matt Green. I took over as director of this center about 3.5 years ago. We crafted these mission statements, which are, I think number one, we're well positioned here to be recognized as an international leader in this space of developing negative emission technologies. Secondly, we focus on a range of activities from fundamental science, studying molecular mechanisms of how different materials to capture CO2 work, to scaling them up. And I'll tell you more stories about some of our technologies at scale recently. You'll also hear from Stephanie later about work that's at this regulatory and new principles of carbon accounting interface later on. We also have a lot of activities focused on reaching out to communities and engaging in dialogues to understand how these technologies affect them, their energy grid, their water security, and what those technologies should look like from their perspective. What do they want? And so we do this across length scales, like I said, from the molecular length scale to the pilot scale. And we are also in the process of launching a new student training platform, a certificate program focused on carbon management and basically this evolving new carbon economy. So our technology deployment efforts are kind of widespread. We have some technologies that are looking at the integration of carbon capture with fuel production and looking at thermal recycling inside those systems where we can move heat around. in different processes. We're working with a number of different startups. You'll probably hear Gary talk about this later, to understand how we can scale these technologies and couple it with permanent storage injection and permanent storage. We have technologies that use solid sorbents and liquid sorbents. So these are kind of two different classes of carbon capture technologies. So one example of our liquid sorbent, I'm going to, like I said, if I move down here, I'll lose the mic, but in the bottom center there, there's a subtitle that says DAC and data centers. So we've developed a liquid sorbent technology that would integrate with the air handling system of data centers and then use the waste heat coming off of the CPUs to regenerate a sorbent material. We also have integration technologies that couple with biological utilization. So we can have a carbon capture technology that pulls CO2 out of the air onto this rotating belt here at the bottom. And then as it dips down into an algae bath, it releases the CO2, and you can engineer those algae to make a variety of different things like biodiesels, pharmaceutical products, or you can just grow up biomass as well. Two case studies that I want to draw your attention to. If you weren't here last year and didn't get to hear about the mechanical tree, I'll walk you through that technology now. So you heard Klaus talk about passive technologies. So again, within direct air capture technologies, you can have passive systems and active systems. Our definition of that is an active system. You use forced air where you have fans and blowers moving the air around. That comes at an energy cost. And a passive system, you rely on wind convection to deliver the CO2. And so Klaus had designed this capture system here, that is a cylindrical column with a series of stacked discs, each one housing different sorbent materials. As the wind blows, it delivers the CO2 to that sorbent material. And then just like a slinky, the toy that tumbles down the stairs, you can collapse that back down into a regeneration chamber at the bottom. And so here we show some photos of the system in operation. This was ASU calls this our open door event. So as a community outreach event, I was really excited because I got to show my daughter. That's her head at the bottom of the photo there. So she was really excited to see what I had been working on. And more excitingly now, what we've done over the course of a couple of years of running this system is begin to understand how things like the ambient relative humidity, the wind speed, the ambient temperature affect the amount of CO2 that we can pull out of the air, which allows us to do two things. One is optimize the operation of this system with a set of local environmental and ambient environmental conditions, but also begin to think about where the optimal location to put this technology is, because as it was said before, the beautiful thing about direct air capture is you can put it where it works. You can put it where you can use that carbon dioxide. And so one other technology that I want to quickly highlight, this is something that, in full disclosure, my student and I are in the process of spinning out, is where we can rethink about the sorbent materials that we're using inside of these systems. So designing carbon capture systems that use petroleum-derived feedstocks to then capture the CO2 there's some irony built into that. So this system uses different kinds of materials that we can source from either waste plastics or biomass or other sources. So we use carbonized fibers. We impregnate those with carbonate salts, and we can develop these sorbent materials with unique morphologies. We've shown that these are stable out to multiple cycles, and this chart could go on for many, many yards now. We've taken this material out to hundreds and hundreds of cycles now, and we've built a bench scale system that can capture about 2 to 4 kilograms of CO2 per day at a low pressure drop. And so we're in the process of now designing larger systems, containerized systems that are modular, that are amenable to this idea of mass manufacturing that Klaus has talked about in his slides and in his talk as well. So with that, thanks for your attention, and I'll kick it back over to Martin.
Great stuff. So we have time for some questions. To any of the panel. Please, Amanda, please, yeah, crack on. But please think about questions. We're going to come back to everyone in a second. Please, Amanda. Oh, I've got the roving mic. Hang on.
As the non-scientist in the room, but somebody who arrived at ASU a complete climate despondent, I cannot tell you how excited I am to hear about these solutions. So I have a question for each of you. So Edda, I want to know $30 a ton. That's amazing. That's like one of the silver bullets ready to go. What do you need to go to scale? Francis, I drove through Cornwall yesterday and was shown some of the old mining sites that have now turned into beautiful regenerated forests. What are some of the sociological issues that you're thinking about and environmental? And what might solutions be to those so you can access that second largest in the world tungsten deposit? Friedrich, very interesting to see, you know, like that's amazing. If you think about 4 gigatons a year, what do you guys need? Why is it not happening? And Matt, you've got so many solutions going on in the ASU lab. Which one do you see as most ready to go to market? And how can this diverse group kind of help get to scale for you? Or is it initial grant funding that you need? Thank you.
Questions? Okay, we'll take it in turn. Edda.
This is working already. Okay. Thank you, Amanda. Yeah, $30 per ton, it's quite an achievement. I agree. Just to repeat what I said earlier, it's you know, four point source emissions that are rather concentrated. So what do we need? Well, we need more projects. We need more sites across the world. We need commitment from industry to be willing to invest, and we need investors to just assist. Why are they not investing? I mean, that's a very good question. But yeah,
Please.
So the $30 a ton seemed to be based on you already having a pure stream of CO2 you can sequester.
no, that's not correct.
So the full
The capture-
value chain cost
Yeah.
from capture through to storage is $30 a ton.
Yeah,
Okay.
exactly.
And what are the barriers then to scaling up? Because getting to your question, I mean, where are the barriers? If we could do this now and you've got the storage ready to go and it's there, what are the logistics? What is the problem in us getting this to scale?
Yeah, as I was saying, we need funding to take this to scale. And then on top of that, we also need more efficient permitting, because I mean it takes too long to develop a site from start to once you become operational. So I would say that these are the two main barriers. The technology is there, and it's already very efficient.
And are you looking at permitting in national jurisdictions or in areas beyond national jurisdiction in the area, seabed area, which would be the international seabed authorities?
Yeah, no, so this is different from a country to country. Of course, in Europe we have more or less the same framework. So I'm referring to that. We've been part of the European permitting framework for a long time now, and it's too inefficient. You need to go to I don't know how many different bodies to get different permits. It should be a one-stop shop, as everybody keeps talking about, but somehow we're not making the progress that we want to make. I'm really hoping that sort of with at least some signals from Brussels that we will see a good change there. Then, of course, if we look beyond Europe, whether it's towards North America or other parts of the world, then it's also rather bizarre, but at the same time understandable, that for the same implementation of a certain technology, you just have very different, permitting processes, approval processes, etc., which is then also complicated for not a larger company than we are. So I would really want to see improvement there, and then as I started with, investors to jump on board. It's not a silver bullet, even though Amanda used that term, but it is a critical part of the solution. We need it for certain industrial sectors, for sure.
Just one more quick question before we move to Francis.
That is, in fact, a stunningly low price. What is the source of the CO2? What is the point source you're capturing from?
So these numbers are from our geothermal power plant. So, and the concentration of CO2 is, if I remember correctly, around 50%. So I mean, there are more concentrated emissions out there, but it's because of this highly effective one-step capture injection process where we are directly dissolving the CO2 into water. We don't need to purify it as is done in third-party technologies. It just goes directly into the ground.
Okay, thank you. That's brilliant set of questions. Thank you. Francis.
Yes, so I'm picking up the question about driving through Cornwall, seeing beautiful forests with the historic engine houses. They're quite tall, kind of iconic. You'll see them on lots of symbols for Cornwall engine houses. Right, so I'll pick up, and there's loads of environmental and social discussions we could talk about, but let me first pick up, when you see the historic engine houses, that means that they were mining underground. So that's a really important point to make, is those minerals might be coming from hundreds of meters, or in the future even more, veins underground. So you can potentially have your forest on the top and your minerals from underground, and you can choose where then you get into the underground. And there are examples coming from, say, Anglo-American, where they're putting 5-kilometer long tunnels to get down underneath nature sites so that they leave the valuable nature site where it is and come down from an industrial site outside. So this is exciting, looking at what happens in the future. Some, like South Crofty, is reopening the old mine site, so they will be going down the same shaft that they've used, you know, for hundreds of years, and refurbishing all of that. And then there's technology that says you don't build a mine, you take a drill hole and you take out water, brine, that's got lithium in it, and therefore your footprint is just like a big barn, if you like, a small industrial unit in the corner of a field. And then there are what we call open cast mines, so quarries. And some of those are in the old China clay quarries, so they're already quarries, and then they'll dig down deeper to get to lithium. And then the tungsten one you picked on, that is really a new open pit. It was open from 2015 to 18 on the site of an older pit, and then they made it larger. That's a big footprint of a modern open cast mine. They got their processing wrong, so they closed, now trying to reopen. And around all of these areas, they're all big landowners. And so there's a big discussion about how you create the opportunities. So maybe you have to have a processing plant or an entrance somewhere on fields, or maybe in an old industrial site. But what is the biodiversity net gain overall that's required in planning now? And in fact, we've done a big, what we call a strategic environmental assessment, to look over the whole region and see what the combined impacts would be and the combined opportunities of that. And that is really one thing we're picking up in our research with the local companies and the regional government, is how you can have those discussions in a deep and meaningful way with the local people, and then how you get the development that actually they want and that benefits everyone and will make money for the operators too.
Okay, follow-up question.
Thank you. So for the critical mineral supply, there's been a lot of debate about deep seabed mining and whether it's got a role to play or not, with plenty of suppliers and manufacturers saying they're not going to use minerals from the deep seabed mining supply chain, that they don't see it's necessary for critical minerals, but the whole basis for the investment being based on this is critical minerals, and it's removing pressure on land. Can you just tell me your perspectives on that?
Yes, I guess a very easy one is to say there are enough resources on land if we're prepared to use them on land and do it in the right way. We don't need, at the moment, the minerals off the bottom of the ocean. And of course, the problem is that although the proponents for deep sea mining say, well, look at the mess you've caused on land. Well, yes, so we need to sort that out. But we don't really understand what sort of problems might be caused under the ocean, because from the very deep floor, it's like a desert. You disturb it once, and then it'd be a long, long time for it to regenerate. And so I think I like the science of actually understanding more about the deep ocean floor. Lots of good science to be done before going ahead to mine. And that is the position of many countries and companies, and was almost a de facto position until maybe this last year, when you can see certain governments and some companies actually making some traction to go around the International Seabed Authority. And that's got lots of problems. You know, the ISA's got lots of problems. You can see these people moving around, going around, and they could go and start, and then that's it. Then we'll have a real experiment to watch. So I think the situation's changed in the last year on that.
Just to add to the biodiversity issue in Cornwall, just the point is that you know, the whole of the UK was covered by a temperate rainforest, you know, thousands and thousands of years ago. There are still bits of that rainforest in the relatively hard to get to deep valleys in Cornwall. They call it the Atlantic temperate rainforest. And so it's not hard to find a place, you know, and these are places which are thick as you can imagine of life, huge biodiversity, plants on plants on plants, trees on trees, just astonishing. And there are still bits. So maybe when we reconvene in years to come back here for the New Carbon Economy Consortium, we'll have a little check through that. But thank you, Francis, for doing that. Friedrich, please.
So yeah, what we need, I think we need more brave and long-term perspective having people. I think the long-term perspective is important to see really that some things we are currently doing and just painting them green, they will not work in the future, that it's not the solution. You can just replace, if you imagine economy like an engine, of course you can replace some wheels and make them green and replace them. But I think we are now at the phase where we really have to replace whole compartments and we have to invent new compartments. And this, of course, needs bravery because, I mean, shooting with a silver bazooka, you need to be brave. But on top of that, of course, we need money. So to build a carbon fiber fabric would cost a few millions, which, okay, it's millions, but it's much cheaper than building a new iron work fabric. Yeah, I mean, this is 250 million euros. So it's definitely a magnitude lower. On top of that, the idea or the next step would be to go to the global south because, as I said, it's low tech. You don't need these very complex infrastructure. So we can install it in the global south. And on top of that, the global south is also, it's possible to create this carbon certificates to have an additional revenue out of this process. And regarding the global north, the challenge here is that to invent a new material, which is completely new, it's not just an update. You need a lot of certificates and you have to go through a lot of processes, which you as a startup has to pay, and this is hard. And but nonetheless, I just want to tell one short story. So we not only developed this wall, we also developed carbon fiber stone railway slippers. And there was a new testing unit in Germany where they tried to simulate the load and the usage of the slippers for 30 years within only 5 months or something like that. And normally you can see after this 5 months, how would these slippers look like in reality after 30 years. And normally if you use ferroconcrete slippers, they are starting to get in cracks, etc. And so they have tested this testing unit with normal slippers, and then we put into this testing machinery the carbon fiber stone slippers. And after 30 years simulated, or after 30 years of simulation, we found really no crack at all. So we don't know when this material will lose its strength. And even if you then really try to push this testing unit to the maximum of testing and trying to crack the slippers, we didn't manage it. So they are still available. You can see them.
One is, I like the idea of looking back and looking forward. Right? So, and you explained it really lovely that when sort of concrete was established as a significant building material, it allowed a whole load of new things to happen.
Yeah.
Right. So 2 questions really. If your material was around at the same time as concrete, would you have won that race and concrete just wouldn't have happened? Right. And the next question is
probably
what can you do that concrete can't do?
The point is we still don't know because we are still trying to compete concrete so when we test different things, we see it's similar in its performance and sometimes it's better. And we are always surprised how well this material performed in these tests. So, I mean, just imagine of architecture, which is of buildings which have only half of the weight. I mean, you can think of completely new design and yeah.
Fascinating. I mean, it does remind me when graphene was discovered. When was that? 20 years ago, something like that. And everyone was amazed by it. You know, there's a single molecular layer of carbon. And then there was a sort of question of, well, what are we going to use it for?
Yeah.
And like, well, clearly it's going to have uses. And so there was a huge centre in Manchester that's really dedicated to understanding that, and of course other global centres as well. So maybe that's the sort of approach that's needed, having this amazing new material that seems kind of indestructible, carbon negative, right, and full of strength. Maybe we just need that approach to it.
Would be nice.
Yeah, okay, well, so that. Matthew, do you want to just continue on what I can't remember what Amanda asked you now, but I'm sure you've got a record of.
Yeah. So the center's been kind of strategically focused on a range of different technologies for a couple different reasons. I think one is, if you look at the market potential of any of these given applications, they could be fairly small with opportunities for growth. But I think that the point being that we're going to see many of these technologies, carbon capture within many of these different sectors, grow. And so, you know, getting our ideas into those different sectors is important. But relatedly, you know, where these technologies are deployed, they have different workforces available, they have different energy grids, they have different resource constraints, et cetera. And so, you know, having a diversity of carbon capture technologies available for deployment is also very important. And I think, you know, what do we need? Yes, funding and a stable funding climate, I think, is also important. But beyond that, and I think maybe it ties back into the question to Edda, is a stable regulatory environment that allows the carbon market to grow and evolve is very important for, I think, for all of us. Absolutely.
Okay, another question, please.
Thank you. I was very interested around the carbon capture being used by algae and then into synthetic fuels and so on. Now, obviously, that doesn't remove it from the atmosphere because it's just cycling. But it does have the potential to disrupt and displace fossil fuel sources in the marketplace. So, what do you see as the balance then to drive the change we need between actual permanent sequestration versus reuse technologies?
Yeah, that's a good question. So I think that there's a transition for carbon recycling, essentially, that there's a period where we can rely on that because the margins for a lot of products that can be produced are much higher than they are in the case of capture and storage. So I think that there's maybe like a market angle there where we can say we can absorb some of our higher costs early on by using these carbon utilization technologies, which allow us to sell products at a higher price. And that allows us to come down the learning curve and get to the point where we can then scale very low cost technologies that are amenable to storage. So I think that's one angle to look at it. Yeah.
Well, thank you. Okay, do you have a question over here? Yeah, please, hang on. Nearly at coffee, so you have to be cool.
Thank you very much. I guess it's a question to Matt, really, but it follows on from something that kind of came up multiple times in Klaus's around the kind of modularity and, you know, thinking about these passive approaches. One of the obvious challenges is that you've got small amounts of CO2 stored all over the place in that situation. But you made the really exciting point, I think, that, you know, if that's co-located with a use case or something, there's an opportunity there. Do you see it as more of a cost or an opportunity? And what are the opportunities for that kind of distributed sucking of CO2 out of the atmosphere?
Yeah, great question. I see it as an opportunity, I think, as a way to manage capital costs of these systems and also to have the ability to deploy on a rapid timescale, right? So our construction projects aren't likely to be 10-year projects. That can be much faster, and they can come on and grow because you can install one unit, next unit, and so that's, I think, an opportunity. And so there is, the use case has to be well defined, right, for that given location, whether it's a geology or a fuel production system or whatnot. That use case has to be well defined for that project from the beginning.
Okay, wonderful. We're nearly at coffee. We haven't got time for questions anymore. Apart from this, and we need to wrap up. A sentence each, no more than a sentence, of what you would like us and your audience to take home from your message. One sentence each, please.
I think it's that the solutions exist. They're ready to be deployed at scale. So let's do it.
Thank you. Francis?
Yeah, I guess lots of exciting opportunities for sustainable development around critical minerals. It's just not just the hand-wringing of the tariff wars. It's a really important opportunity for people around the world.
That was a long sentence. Very good. And Friedrich?
Use the cost-effective silver bazooka.
Yeah. Matt, please.
I think I would echo that. And maybe specify direct air capture solutions exist, and there's a number of application spaces where they can be deployed.
Thank you ever so much to the four of you for starting us off on our journey over the next 2 days. Edda Aradottir, Francis Wall, Friedrich Bohn, Matthew Green. Please, round of applause. Wonderful.